Welcome to video on solutions to LMRF Test 1 paper. Now the first question was on triple fat timer monostable multivibrator and stable multivibrator. The first question was, why does the pulse width of quasi-stable state in monoshot vary with VTH? And you are asked to plot the waveform across the capacitor assuming a valid trigger signal. And it was also said that let VCC be 8 volt and VTH is equal to 4 volt and R is equal to 1 kilo ohm and C is 0.1 microfarad. So the answer is the pulse width of a quasi-stable state in monoshot depends on the time taken by the capacitor to charge from 0 volt to VTH, because as the value of VTH varies, so naturally pulse width has to change. And the answer is, why does the pulse width changes is because as the capacitor voltage is asked to change from 0 to VTH, which decides the pulse width of the quasi-stable state. So naturally, as VTH changes, the pulse width should also change. And for this given specification, we are asked to plot the voltage across the capacitor and the output waveform. So now we are considering a valid threshold trigger signal where it is going below VTL, and as soon as it goes below VTL, the capacitor starts charges from 0 to VTH. Now since it is started from 0, the VTH given is 4 volts, and we know that during that charging period the monoshot is in quasi-stable state, so this is the pulse width. Output voltage is 8 volts during quasi-stable state. During stable state it is 0 volts. Since the VTH is not 2/3 of VCC, so we have to consider an equation corresponding to the pulse width, which is not 1.1 RC. Now it is no more 1.1. Now it is ln of natural log of VC by VCC minus V external. So since this V external is 4 volts, that is VTH is equal to 4 volts. So we'll actually get the expression for the T pulse width happens to be 69.3 microsecond. So it will not be 1.1 RC, it will be actually 0.69 RC because ln of 2 is 0.69. Next question was, during the stable state of monoshot, what are the values of R and S of the flip-flop, what are the output voltage and transistor condition. Now we know that when you are in a stable state condition, the output of the flip-flop, output of the monoshot will be 0 volts, and since the trigger voltage is always greater than VTL for a stable state, the capacitor voltage will be 0, and we're going to have the R and S happens to be in 0 condition. Now since capacitor voltage is 0, so it is possible only when the transistor is on. We know that the transistor is getting the base drive from the opposite of Q, which is since Q is 0, Q bar is 1, so transistor will be on. Whatever voltage that is stored in the capacitor will be discharged to 0. We're going to have R is equal to 0 and S is equal to 0. The third question is, write the signal conditioning circuit for the trigger signal shown in figure 3. Obtain the valid trigger signal to obtain the pulse width of 1 millisecond. Assume no external voltage is applied to the control voltage of triple five timer. The figure 5 is figure number 3 is this. So as you can see here, it is on time is 2 millisecond and off time is also 2 millisecond. Since we want to have a pulse width of 1 millisecond, we cannot apply this directly to the monoshot, because since it is at minus VCC for almost 2 millisecond, as the period of the pulse width of the monoshot is only 1 millisecond, and the trigger signal has a voltage less than VTL for 2 millisecond, which is more than the desired pulse width. Suppose if you apply it as it is, so we're going to get a quasi-stable state of 2 millisecond. So hence there is a need of signal conditioning network. Hence there is a need to condition the signal before you apply to the trigger pin of triple five timer. So we need to generate the spikes now. So the signal conditioning circuit should generate spikes, and signal should be less than VTL for a small duration of time, that is it should be less than 1 millisecond. So this is a signal conditioning network. So this RD and CD will going to generate the spikes, and this diode will going to make sure that this positive spike is being limited to only V gamma, and this VCC will ensure that it is clamped to 5 volts. So you can see now this is a trigger signal, valid trigger signal. From this type of square wave, you could able to reduce it to a spike type of trigger signal. Now you can see the spike is going below VTL. So once it goes below VTL, so the output goes to quasi-stable state, remains for 1 millisecond and then comes down. The design here is RD into CD, because as you can see here, this RD into CD is working like a differentiator. For generation of spike from a square wave, we need to have RD into CD should be far less than the time period of this pulse, which is 2 milliseconds. So RD into CD should be far less than 2 milliseconds. So I am writing this far less as 0.01 times 2 milliseconds. So we'll get some value. So assuming the value of CD to be 0.01 microsecond, the value of RD comes out to be 2 kilo ohms. So this way we can have a signal conditioning network which will generate the spikes which is of desired trigger signal. The next question was design and write a triple five timer or stable multivibrator to generate 1 kHz 10% duty cycle. Assume no external voltage applied. Since it is 10% duty cycle assumed, so of course given, so we know that T on is given by, because now since the pulse width is less than 50%, so we have to use a diode so that this diode can be used to bypass this RB while charging. So the expression for the on time and off time is given by these two expressions, and we know that total time is given as 1 kilohertz means 1 millisecond. The on time is total time multiplied by duty cycle, which happens to be 0.1 millisecond. T off is 0.9 millisecond. So assuming the value of C to be 0.1 microfarad, we can get the value of T off as 13.043 kilo ohms. Similarly, by substituting the value of CT onto this T on expression, we'll get the value of RA as 1.44 kilo ohms. So this diode is a must because we need to have we need to bypass this RB during the charging time. So the expression is for T on is through RA, for T off it is through RB. And next question on the same topic is, what is the maximum and minimum on time of a regular triple five timer or stable multivibrator when external voltage is applied? The control voltage of triple five timer is varied from 4 volt to 1 volt. And assume VCC as 10 kilo ohms and the values of RA, RB and C are given. And you are asked to comment on the off time of this triple five timer, so during both the conditions. So we know that the on time is given by, because it is given as normal circuit, so we are going to include RA, RB during the on time during charging. So RA plus RB into CT into ln of, since we are having an external voltage which is 4 volt, so this is a general expression for VTH to be 4 volt. By substituting the value of RA, RB and C of T which is given here, we'll get the on time for for VTH of 4 volt as 163.9 microsecond, and the same on time for a VTH of 1 millivolt happens to be VTH of 1 volt happens to be 30.81 microsecond. So this way the on time changes, but surprisingly we can see that the off time, which is 0.69 RB into CT, is independent of the VTH. So that's why this VTH is the off time is constant for both the voltages. Only there is a change in the on time from 163.9 microsecond when it is 4 volt, and when VTH is this is actually VTH. When VTH is actually 1 volt, it is minimum, that is 30.81 microsecond. The next question is an interesting question. An inverting Schmitt trigger suggests the modification in the basic circuit without using V reference, such that VTH is equal to twice of magnitude of VTL. So assume VTH plus or minus V set as 12 volt and VTH is equal to 4 volt and VTL is equal to minus 2 volt. Now this you can see we have been asked to realize this circuit without using a reference voltage. So without using reference voltage, if you want to have two different threshold voltages, we are supposed to have two resistors. One is for higher threshold voltage, other is for the lower threshold voltage. So that will be controlled using the diode. As you can see here, the diode D1 will be on when the output voltage is negative, the diode D2 will be on when it is positive. So similarly, the expression for the VTH happens to be, which is 4 volt is equal to plus Vsat, that is when the output voltage is plus, it is R1 divided by R1 plus the diode D2 is on. The corresponding to that we won't have this R2TH. So I am writing this as R2TH. And similarly for the expression for VTL, the D1 is on. The expression for VTL happens to be minus Vsat R1 divided by R1 plus R2 into TL. Sorry, R2TL. So we have named this resistor as R2TL, this as R2TH. So instead of writing it as simply R2R2, we are differentiating this as R2TL, which is responsible for the lower threshold, and R2TH responsible for the higher threshold voltage. And plus or minus Vsat is given as plus or minus 12, and VTH VTL is given. So by assuming one of the resistance value, that is R1 is equal to 1 kilo ohm, using these two equations we can find what is R2TH, which is 2 kilo ohms, and R2TL happens to be 5 kilo ohms. So this way we can get different threshold voltages even without using the reference voltage. So we need to use, because it was said that you are allowed to use any component for modification, we are using two diodes to modify the circuit. And here write the output waveform for a non-inverting Smith trigger with VTH is equal to minus 2 volt and VTL is equal to minus 6 volts for the following input waveform, which is a sawtooth waveform. And the input amplitude is given as minus 8 and plus 8. And please write the output waveform by taking the input waveform to reference. So we have taken the input waveform as a reference. Here you can see it is ranging from starting from minus 8 going till 8, and it is falling quickly and then it's again going. So this is how the transfer characteristics looks like. Suppose if you want to write this output characteristics, just have a look at when the input is minus 8 volt, that is when it is minus 8 here, the corresponding output is minus Vsat. So we have written here when it is minus 8, the output voltage is minus Vsat. So we know that it makes a transition from minus Vsat to plus Vsat only when the input voltage goes below, that is when it is becoming minus 1.9, then only it makes a transition. So this will be still in minus Vsat till it is minus 2. When the input voltage goes anything more than that minus 2, so that is magnitude wise it is more than that, you can see the output is making a transition from minus Vsat to plus Vsat. That is, we are going from here to here when the input voltage is minus 1.9 somewhere. So it's here. So it is making transition. Now you can see during the input voltage, which is 0 and positive half cycle, the output voltage is, you can see, output voltage plus Vsat, we have it as plus Vsat. And you can see the input voltage is dropping directly from 8 to minus 8 immediately. From 8 minus 8 it drops instantaneously. So during that time there is a minus 6. So this minus 6 is somewhere here. The output makes a transition from plus Vsat to minus Vsat. As you can see here, it is now going from plus Vsat to minus Vsat directly, and it remains in minus Vsat till minus 2, and then it again goes up. So this way you can write the output waveform. So taking this input as a reference, only at minus 2 it makes a transition from minus Vsat to plus Vsat. So during this point it is making a transition from plus Vsat to minus Vsat, because during this period itself the output is crossing minus 6. And you are asked to write the expression for the voltage gain of an op-amp when it is used as an astable multivibrator. As you can see here, this is a stable multivibrator. So there is a positive feedback given to increase the gain here, because we know that a stable multivibrator has got its output voltage plus Vsat and minus Vsat. So it has to be a positive feedback. A0 is the gain of the amplifier under open loop. When you are providing a positive feedback, the gain is going to further increase. So gain is given by A0 divided by 1 minus A0 into beta, where beta is given by R1 divided by R1 plus R2. So this is the expression for the voltage gain of the amplifier in positive feedback. And write the expression for the maximum and minimum voltages of the capacitor used in a stable multivibrator. Does it change? Does this vary with the charging and discharging time constant? We know that the capacitor will vary from minus beta Vsat to plus beta Vsat. The expression for that voltage is it is plus beta Vsat and minus beta Vsat, and it does not vary with the time constant.